Here we're given f of x comma y over the region defined here, where the region D is x squared plus y squared less than or equal to 9. We're asked to evaluate the given double integral. Notice how this double integral is given in rectangular form. We're actually going to convert this to polar form to determine the value of this double integral. But let's first take a look at the region of integration, the region x squared plus y squared less than or equal to 9. We should recognize that x squared plus y squared equals 9 would be a circle centered at the origin with a radius of 3 shown here, and because we have the inequality x squared plus y squared less than or equal to 9, the shaded region here is the region of integration. Next, we're converting a double integral in rectangular form to polar form. We need to write the function f of x comma y as f of r comma theta, so we need our function f to be a function of r and theta. We do this conversion using our formulas provided here, and then differential a, which in rectangular form would be dx dy or dy dx, in polar form converts to r dr d theta. So it's important to remember we have an extra factor of r here when converting to polar form. And then of course we have to find new limits of integration in terms of r and theta. So before we set this up though, let's look at this graphically. The function f of x comma y is graphed in blue. And again, the region of integration is this circular region here in the xy plane. Because the function f of x comma y is non-negative over this region, our double integral is going to give us the volume under the blue surface above the xy plane over this circular region. And notice how this actually is going to be half of a sphere, so we could evaluate the double integral using a geometric formula, which we'll do to check our work after we determine the value of the double integral. So going back to our work, notice how the given function f of x comma y is equal to the square root of, let's write this as 9, and then instead of minus x squared minus y squared, let's write that as minus the quantity x squared plus y squared. Which means our function f of r comma theta in polar form would be equal to the square root of 9 minus r squared, because remember, x squared plus y squared is equal to r squared. So again, we have the double integral over the region D of f of x comma y, which would be the square root of 9 minus x squared minus y squared, and we have dx dy. In polar form would be the double integral. The integrated function again is f of r comma theta, which we now know is the square root of 9 minus r squared, and then we have r dr d theta. And now we need to determine the limits of integration that would trace out the region of integration. So we first want to find the limits of integration for r. Well, because this is the region of integration, r is going to be from 0 to 3. So with respect to r, we integrate from 0 to 3. And then for the limits of integration for theta, to trace out this region, they would have to be from 0 all the way to 2 pi radians for 1 full revolution. So the limits of integration for theta are from 0 to 2 pi. Now let's go and evaluate this double integral in polar form on the next slide. Notice how to find the antiderivative with respect to r, we'll have to perform u substitution. So we're going to let u be equal to 9 minus r squared, and therefore differential u is going to be equal to negative 2r dr. Notice how we have r dr here, so let's go ahead and divide both sides by negative 2. So we know that negative 1/2 differential u is equal to r dr. So let's write all this in terms of u to help us find the antiderivative. Because u is equal to 9 minus r squared, this would be u to the 1/2. And then r dr is equal to negative 1/2 du. The antiderivative with respect to u would be negative 1/2 times u to the 3/2 divided by 3/2, or instead of dividing by 3/2, we can multiply by 2/3, which means the antiderivative with respect to r would be negative 1/2 times u to the 3/2 is really 9 minus r squared to the 3/2. Then instead of dividing by 3/2, let's multiply by 2/3. Notice how here this simplifies nicely to negative 1/3. So we'd have negative 1/3. And then when r is equal to 3, we have the quantity 9 minus 3 squared to the 3/2. Minus, when r is 0, we have 9 minus 0 squared to the 3/2. Now simplifying, with a double integral from 0 to 2 pi, and we have negative 1/3 times, here we're going to have 9 minus 9, which is 0 to the 3/2, which is 0, then minus 9 raised to the power of 3/2. 9 to the 3/2 is equal to 27, so we have a negative 27. Well, negative 1/3 times negative 27 is equal to 9. So we have the integral from 0 to 2 pi of 9d theta. So the antiderivative is 9 theta, which we can write as 9 times theta. So we have 9 times 2 pi minus 0, which equals 18 pi. And again, because our function is non-negative over the region of integration, we just found the volume of this half sphere. And let's check our work using the volume formula for a sphere. And we should be able to tell from f of x comma y, the sphere is going to have a radius of 3, same as the radius of the region of integration. So because the volume of a sphere is equal to 4/3 pi r cubed, and our double integral is equal to half the volume of a sphere, so we would have the volume is equal to 1/2 times 4/3 times pi times r cubed, where r is equal to 3, so we have 3 cubed. Notice how this simplifies. So we have the volume is equal to 2/3 pi times 3 cubed, which would be 27, or 27 over 1. Again, this simplifies. So 1 3 and 3, and 9 3s and 27. Notice how we get the same result. We get 18 pi, which again is the volume of our half sphere, so these would be cubic units. So using the geometric formula, we found the volume to be 18 pi cubic units, which is the same value we found using the double integral. In many cases, we won't be able to verify our double integral using a geometric formula, but in this case we can. I hope you found this helpful.